Greetings, physicists, and welcome back for your chapters 11 and 12 lecture video. Today we're going to be talking a little bit about atomic structure, but there were also a couple of other important topics that were too important for us to pass up. And I apologize for the sort of goofy formatting of these two chapters, but we're going to try to get all of the important pieces at the very least. We're going to begin today with sort of a history lesson, a short history lesson, so we can sort of set the stage for our understanding of atomic structure. The ancient thinkers proposed for millennia that there is a fundamental size for matter, something smaller that cannot be divided any further. And that is where we get the root of the word atom, which means indivisible. Although we know now that atoms are made up of protons, neutrons, and electrons, and those protons, neutrons, and electrons, what we call our elementary particles, are actually made up of smaller particles called quarks. And there is even some evidence that quarks are made up of something that we don't even understand yet. However, atoms are the lowest form, the smallest form of stable and electrically neutral matter that shows differentiation in characteristics. The characteristics that we normally call elements: hydrogen, helium, oxygen, those kinds of things. So let's start there with atoms. A physicist named Robert Brown saw that tiny particles of pollen, which originally led him to believe that it was life responsible for this phenomenon, but he saw that tiny particles of pollen and dust and soot and whatever, when they were suspended in a fluid like water or air, all seemed to move around randomly. Nowadays we call this Brownian motion. Albert Einstein was able to explain this phenomenon in 1905, showing that molecules, which were of course made up of atoms, molecules, things like water, right, which is made up of 2 hydrogen atoms and 1 oxygen atom, do in fact exist. And this is a big thing. This is back before we knew about molecules and atoms and all this stuff. And as a result, eventually he was accredited with a discovery that was worthy of a Nobel Prize. But also in the same year, he came up with special relativity, which is parts of the famous theory of relativity that he used to describe gravity, and also another thing that he called the photoelectric effect. And because all 3 of these things were eventually decided to be Nobel Prize worthy, they called the year that he figured this out, 1905, the year of miracles. But how small are these things, these atoms? Well, we probably really have no intuitive sense of how big a number like 10 to the 23rd actually is, because that's like writing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 21, 22, 23. There is nothing in our daily lives that has this many zeros in it, right? Even the richest people don't have this kind of whatever in their bank accounts. We don't travel that many miles. We don't think about the distance that we travel in tiny little microscopic units. And so trying to relate a number this large to something is, maybe a little counterintuitive. But if you had 6.02 times 10 to the 23rd atoms of, say, hydrogen, then you would have 1 mole of hydrogen. Okay? If you have 1 mole of hydrogen, because hydrogen has an atomic mass of 1 mole of hydrogen has a mass of 1 gram. The atomic mass of water is 18. Oxygen is 16. Hydrogen is 1 each for a total of 18. And if you had 1 mole of water, or 6.02 times 10 to the 23rd water molecules, you would have 18 grams of water. Now that's not a tremendous amount, because that's not enough to drink, right? 18 grams is about 18 milliliters or 18 cubic centimeters, and 1,000 milliliters or 1,000 grams is a liter of water. That's enough to drink, right? Now the book makes the comparison. A mole of apples, or 6.02 times 10 to the 23rd apples, is about the number of apples that you would need to fill the Earth. And even stranger than that, most atoms are mostly empty space. If you take, for example, the hydrogen atom. The hydrogen atom has one proton, one single proton in its nucleus. And then way out here, there's one electron in the ground state orbital, which is actually like a sphere. And electrons are kind of funny. They kind of appear to be everywhere in this orbital all at once. In any case, if you were to try to blow up the hydrogen atom to a sufficient size, if you're trying to scale the hydrogen atom to a sufficient size such that the single proton in the nucleus was the size of a penny, this orbital would be about the size of the moon. And all of that space in between is just empty space. There's literally nothing there. There's no air in there, whatever, right? You're talking about a tiny little microscopic construct. There's no room for oxygen molecules and whatever to fit in there. There's nothing there. Now, atoms all have protons, the positively charged particles that all have a mass, or an atomic mass, of about 1 AMU, right? Atomic mass unit. Electrons have about an atomic mass of 1/2000, right? They're very small in the mass compared to a proton. Electrons have a charge of -1. Protons have a charge of +1. There's another particle, of course, the neutron, and it has an atomic mass of 1, but no charge. Neutron for neutral, right? In any case, the protons and the neutrons always live in the middle, in the center of the atom, what we call the nucleus. Now, I know what you're thinking. If you have, let's say, we want to talk about the helium atom now, right? Helium has 2 protons. And the standard stable form of helium has 2 protons and 2 neutrons in the nucleus. And then, of course, it has to have 2 electrons, right? In the ground state orbital, the lowest energy level outside of the nucleus. But if these are positive, shouldn't they repel each other? Well, yes, they absolutely should repel each other, and as a matter of fact, they do. But if they repel each other, how is it that they can stay here in the nucleus together? Well, there are 4 fundamental forces in nature. One of them is this funny thing that we call the strong nuclear force, also called the Yukawa potential, named after the Japanese physicist who figured all this out. But if these are close enough together, the strong nuclear force holds the nucleus of the atom together, overcoming the repulsive electric force, the 2 positive charges pushing each other away. But if opposite charges attract, does that mean the protons attract the electrons? Well, yes, they do. Let's go back to the simple case again, the hydrogen atom. Here's our single proton, here's our single electron, and I'm sure we can agree there's a certain amount of attractive force in between these 2, right? We can also agree that if we had this situation, right, where we had twice as much, there would be more of an attractive force, and then maybe the electron orbital would be in a different place, right? It'd be there instead because the gravitational or the electrostatic attraction is so much more intense. And so we can probably pretty plainly see that these electron orbitals, the places where the electrons live, are different for different elements. Interesting, right? So if we double the number of protons, then the electrons will live closer, right? The number of protons in the nucleus of an atom, therefore, give the atom its properties. And this is how we define an element by the atomic number, or the number of protons in the nucleus. As a matter of fact, for a very long time, the periodic table of the elements did not look like it does today. We were finally able to put a much more sensible arrangement together for the periodic table of the elements, once we finally figured out all of these electron orbitals. And that didn't come along until we were actually able to figure out quantum mechanics. And the theory goes something like this. Because there's a certain amount of attractive force in between the electrons and the protons, the energy levels are quantized. So for every hydrogen atom, this energy level, right, where this orbital is always the same. There is a first excited state. We usually call this n equals 1, the ground state. That's the lowest state. There's an n equals 2, and n equals 3, and so on. And for every hydrogen atom, these are always the same. Always, always, always. For those of you who are well-versed in music, you can think of these as like the chords struck by a finely tuned piano. They're always precise, always exactly in the same place. And obviously, these energy levels are going to be different. If this was helium, this might be n equals 1 might be here, and n equals 2 might be here, and so on, right? And so the energy levels are different for every element because of the difference in attractive force. Now, the reason that the periodic table has the crazy shape that it does has to do with the energy levels and also the angular momentum of these orbitals. The farther away the orbitals are, the more freedom they have to express themselves sort of differently, right? There's this also fundamental principle that we call the Pauli exclusion principle that says only one electron can occupy a given state. Now, in the first shell, there's only one electron orbital, but two electrons live there because one of them is spin up and the other one is spin down. And because of a funny thing that we call spin-orbit coupling, basically the spin of the electron combined with its orbit around the nucleus give it a very subtle amount of energy difference if it's spin up or if it's spin down, rotating one way or rotating the other. And so two electrons can live in one orbital. Here at n equals 2, there's spin up and spin down, but there's also angular momentum a little bit this way and angular momentum a little bit this way. So there's 3 possible angular momentum states, each with 2 electrons in it. And so here there's 6, which is why on the very far right hand side there are room for 6 elements. On the very far left hand side there's only 2 and then 6, and then out here there's 5 possible orientations, right? You have 3 degrees or 2 degrees of freedom. And so 2, 2, 2, 2, 2 makes 10, which is why the middle part of the periodic table has 10. And then farther out, beyond n equals 3, out here, you're going to have 3 degrees of freedom, right? So it's -3, -2, -1, 0, +1, +2, +3, or 7 total different angular momentum states, each with 2 electrons in it that are spin up and spin down, and that's why the row across the very bottom of the periodic table has 14 slots in it. crazy, right? By the way, you don't have to know that. That's just done for your own personal enrichment. Um, but that's why the periodic table of the elements looks the way it does. Now, if all of this craziness, all of this stuff that I told you about electron levels and atomic structure and angular momentum, quantized orbitals, and all this craziness is actually true, there should be some kind of proof, right? You remember when I said all of these electron energy levels are quantized, they're the same every time in a given atom? Well, in 1911, a guy named Max Planck, a physicist, won the Nobel Prize for figuring out that the energy in a light packet, what we call a photon or a light particle wave duality, the energy in one of these things depends on the frequency of the light itself. Now, if you're one of these electrons, say this one, right, and you live in this hydrogen atom, you're only allowed to live exactly in this orbital, or exactly in this orbital, or exactly in this orbital. You can't live anywhere in between. We'll come back to why that is a little bit later when we talk about the de Broglie wavelength. But suffice to say, if some light comes up here, some photon comes up here and strikes you, and it gives you just enough energy, the exact amount of energy corresponding to the difference in between these two energy states, this electron can get excited up to a higher energy state. Now, generally, they don't like to stay in an excited state too long if there's an open spot for it in a lower energy state, because that's more stable. And when the electron de-excites, when it goes back down, it's going to emit a photon or some light, some electromagnetic radiation equal to this energy difference again. That, of course, is going to correspond to one frequency, wavelength, color, whatever you want to call it, of light. Interesting, right? Now, because these electron energy levels are quantized, the light that is given off from this transition is going to be the same color every time. And so if you took some gas, like hydrogen, for example, and you bombarded it with tons and tons of energy to try to excite the electrons up to higher energy states so that they would jump back down, you would expect to see colors that only correspond to the transitions in between these states. And indeed, if you take what we call an emission lamp or a gas lamp, and you excite the gas in these emission tubes, you're only going to see a certain number of colors, right? Now, unfortunately, I don't have one of these here at home, but I have included a link to a gas lamp demo and an emission lamp demo, both in the lecture notes and on the page for the lecture. So if you haven't taken a look at it, please do so now. Now that you've seen the gas lamp demo and you've seen what I mean, that there are only certain emission colors that happen as a result of gas getting excited and de-exciting. You've seen that there is some evidence that hydrogen has a different emission spectrum, right? It gives off different colors from helium or mercury, for example, right? They all have their own different emission spectra because their electron energy levels, their orbitals, are at different energy levels. And so they can only absorb and re-emit certain frequencies or colors of electromagnetic radiation or light. In any case, moving on, we know that all matter moves. Even matter in the solid state moves. And it doesn't matter if it's solid steel or, adamantium or whatever, right? The individual particles are also moving, right? They're always moving. The more they move, the higher their temperature. Now, we'll come back to that a little bit later when we talk about thermodynamics, but just know that the kinetic energy, the energy of motion in something that's hot is going to be greater, right? And conversely, of course, if you take the kinetic energy out of a substance, the particles are going to move less, right? And if you take all of the kinetic energy out of a substance, the temperature decreases to 0 and stops existing. We call that temperature absolute zero. We'll come back to that one as well, also when we talk about thermodynamics. But suffice to say, as long as a particle hasn't lost all of its energy, it still exists. And as a result, there's hydrogen, for example, that's been around for almost 14 billion years since the Big Bang, since the beginning of the universe. Matter occurs in nature electrically neutral, and what we mean by that is there are, when something occurs in nature, the same amount of electrons as there are protons in an atom. And in the case of hydrogen, of course, since hydrogen only has one proton, it's going to occur in nature with one electron. Now sometimes the amount of mass can also be different from the normal amount, usually in the form of neutrons. And if a hydrogen atom picks up a neutron, it becomes deuterium or heavy hydrogen. It's still hydrogen because it only has one proton, right? But it has a mass of 2. So we call it something else. In any case, we call that an isotope. For example, the stable isotope of carbon is carbon 12, meaning it has a mass of 12, right? I believe carbon is element number 6. And so it's got 6 protons and 6 neutrons in it. There is, however, an unstable isotope, carbon 14, that has 2 extra neutrons. This unstable isotope decays into carbon 12 with a half-life of 5,730 years. And what that means is that every 5,730 years, half of the carbon 14 in the sample decays into carbon 12. Or something else. In any case, an isotope is an element that sometimes has, a different amount of mass in it. A little more vocabulary. Something called a compound is matter that is made up of 2 or more elements. Things like salt, sodium chloride, right? Table salt. Or water, right? Hydrogen and oxygen. Those are compounds. Carbon dioxide is a compound. A molecule is the smallest particle of a compound, right? Water doesn't exist in an atom. It's 1 oxygen atom and 2 hydrogen atoms, right? 3 atoms make 1 molecule in that case. But you can't just throw 2 things together and expect them to make a compound. You know what they say, oil and water just don't mix. And as a matter of fact, oil and water cannot create new molecules together. Oddly enough, chemists call things like this, like your salad dressing, a mixture. Even though they say oil and water don't mix. In any case, I digress. The book goes on to talk about antimatter, but antimatter is quite rare and exotic. If a particle, like an electron, comes into contact with its antimatter particle, which is a positron, right? It's just like an electron, except it has a positive charge. So we have an electron and a positron. If they meet, they annihilate each other and release a ton of energy. The amount of energy can generally be found pretty simply with Einstein's relation. If you take the mass of these 2 particles, multiply it by the square of the speed of light, which is huge, right? Remember, the speed of light is 3 × 10⁸ meters per second. So you take this tiny amount of mass, multiply it by this huge number, right? 3 times 10 to the 8 squared is 9 times 10 to the 16. So you're going to get 16 orders of magnitude more energy than you would mass. That's a lot. To give you some idea of how much energy that is, if you took 1 gram of hydrogen and you converted it completely and totally into energy by some process similar to antiparticle annihilation, like these two things touching each other and blowing up, it would be equal to about 1,000 Moab bombs, or about the same energy released when the Chelyabinsk meteor hit Russia. That's a lot. Now, the book goes on, and I'm going to pick on the book just a little bit more here. The book goes on to state that about 23% of the matter in the universe is what we call dark matter, and that's wrong. Like we said last time, dark matter is the missing matter in most galaxies, and that's generally probably something like 90%. That's how much is missing. So what is dark matter? Well, we don't know, and that's why its name is what it is. It's dark, it's not giving off any energy, it is or any light, and so it's not luminous, therefore dark matter. If we examine a galaxy's rotation curve, we can see that stars that are farther away move faster than we expect, right? If we're just totaling up the luminous matter, and that's where it comes from. And also dark energy actually comes from the fact that the universe is expanding faster than we think it should be, but let's not belabor the point, shall we? Now, there are two very important concepts in Chapter 12 that we cannot just omit. So we're going to go over them briefly, even though most of the rest of Chapter 12 is kind of a mess. Two things that we need to know for sure are the definition of density. Density is mass over volume. What are some units for density? Well, strictly speaking, the unit that we have for mass is the kilogram, and the unit that we have for volume, well, the unit that we have for length is meter, so meter times meters, right, in 3 orthogonal directions, or 3 mutually perpendicular directions, is the cubic meter. Although kilograms per cubic meter is usually huge, so sometimes, we use something like grams per cubic centimeter, right? And that's actually where we get the old definition of both the gram and the cubic centimeter, because 1 gram of water should occupy, pure water at room temperature, should occupy the volume of 1 cubic centimeter, which is not a lot. In any case, most matter can stretch or compress at least a little. And we take the extreme case of a spring, we can see that if you pull a spring outward, right, if you stretch it out beyond its equilibrium position, then as you pull it out, it's going to pull back inward, right? It's trying to restore itself. And so let's say that this is the spring's equilibrium position. Now if we stretch it out to here, the spring is going to want to compress itself, right? Offering a restorative force. And also if we compress it, the spring is going to want to push outward in order to try to restore itself to its equilibrium position. If we wanted to talk about the amount of force that it's going to offer, there is a relationship for that. Obviously, the farther you pull it, the harder the spring is going to pull inward, right? And so we say the spring force is minus kx, where x, so this would be like x in this case, or in this case, this would be x. It's the displacement from the equilibrium position. We went from here and stretched it out to here. So the distance from equilibrium is this far, right? It's going to push, the minus sign is here to show that it's going to push in the direction opposite the displacement from equilibrium. So if we're pulling it outward, the spring is going to want to push inward, right? And if we're compressing the spring inward, it's going to want to push outward. This thing here, K, is what we call the spring constant, and that's just a measure of how strong the spring is. Obviously, a really strong spring is going to have a higher spring constant than, say, a slinky, right? Now, we should end up with newtons, right? This is in meters. That means the spring constant is generally in newtons per meter. And that just about does it for chapters 11 and 12. I hope you've enjoyed this video. Please contact me, of course, if you have any questions, and I'll see you next time for chapter 13.